Yeah, no, not in a row, but a few breaks in between. And also remember, yeah, I think you had it last week as well. The last lectures moved forward an hour. So that CO14. Okay, but for this first hour, we're back in number theory. We are dealing with this material of polynomial congruences. Just a very quick recap. Polynomial congruences. In chapter 1, we deal with the simplest case of, the simplest kind of polynomials you might encounter. These are the linear ones. Okay? They're not really full-blown polynomials, I guess. They're just equations or congruences of the form ax congruent to b modulo whatever, modulo n. And we're interested in understanding when those things have solutions. And we approached it in a couple of steps, but it kind of culminated in what's being described in theorem 6.3. Theorem 6.3 says you only have solutions. Solutions exist if and only if d, which is the greatest common divisor of a and n, greatest common divisor of the coefficient of a and the modulus, if that's equal to, well, that's equal to whatever it is, equal to some number d. And if that number d divides the constant term b, then there are solutions. If it doesn't divide it, then there aren't. Okay? And in the case where it does, then there exist exactly d solutions modulo n. And this theorem describes nice representatives for those congruence classes. They're of the form t plus I times n over d. The parameter I goes from 0 through d minus 1. This is d cases for I. T is the unique solution of the reduced congruence, because after you divide everything by this number d, that's the greatest common divisor of a and n. So what's left behind, a over d, n over d, those are co-prime. So a over d has an inverse. So you multiply both sides by the inverse, so you get a unique solution to this reduced one. That's your solution T. And then looking at various representatives for that for the congruence class of T modulo n over d generates the d different solutions to the original linear congruence. Okay, so in last week's tutorials we did a few examples of those. Any remaining questions or queries on dealing with linear congruences and using that result? Anything associated to it before we move on? Okay. So we also started to talk about the Chinese remainder theorem last time. And this is an important result. It's going to be useful to us in the next chapter when we're describing the general the solution for a typical polynomial congruence. And Chinese remainder theorem, as it's presented here, talks about how to look at a number of distinct or a number of different congruence classes modulo different moduli, from M1, M2, all the way up to MK. And in the special case where those are all pairwise coprime, meaning that if you take any two of them, they're going to be coprime to each other. If those are pairwise coprime, then this set of congruence classes actually corresponds to a unique congruence class modulo the product of all the moduli. So there's one and only one congruence class modulo the product M1 times all the way up to MK. And everything in that congruence class is a simultaneous solution of all of those. Now, what we'll see shortly is that when we're tackling a general congruence, f of x congruent to 0 modulo sum n, what we're going to use is, we're going to use the prime factorization of n. Let's call this k for the moment, just to match with this. The prime factorization of n is an expression for n as a product of prime powers. Okay? And the pi's are all distinct prime numbers. Then this single congruence is actually equivalent to a collection of congruences. So you get a set of congruences modulo each of the prime powers that are appearing in the prime factorization of n. So you got k of these. There's k distinct prime factors in n. Then the original congruence, which we're going to be faced with and we're going to be trying to solve, can be shown to be equivalent to this set of congruences. So x will be a solution of this first one if and only if x is a simultaneous solution of these. So that will allow us to, instead of trying to solve a polynomial congruence modulo some n, instead we can solve it in these special cases where, and they're simpler in that the modulus is no longer some general type of integer, but the modulus is just a power of a prime. And knowing that structure about the modulus will help us to find the solutions of each of these. Okay? And then once we've solved all of these, what we get is a set of solutions. Each solution is a congruence class modulo one of these prime powers. So let's say a B1 mod P1 to the alpha 1, all the way up as far as x equals, or x congruent to bk modulo bk to the power alpha k. So when you solve all of these, you end up generating loads of solutions, and you can take one solution for each one. You kind of package them together, and as long as x satisfies all of these, it'll satisfy all of these, and so x will satisfy this. And it's the Chinese remainder theorem which allows us to take those and put them together to get back to solutions of this. Okay? Because the Chinese remainder theorem shows you how to take a bunch of simultaneous congruence classes modulo these different moduli, but the moduli are all pairwise coprime. If you take any two of these different prime powers, the primes are different, so there's no common divisor between them apart from one. So these are pairwise coprime. If you take any set of solutions here to these set of solutions here, the Chinese remainder theorem generates a simultaneous solution modulo the product of all those, i.e. modulo n. So it's the Chinese remainder theorem that gets us back to solutions for the original congruence. So that's a lot of motivation for it, a lot of motivation about why we should care about it, and one of the uses we can put it to. The actual technique for finding solutions of these things, modulo a power of a prime, that's dealt with in the next chapter. The particular methods involved there. Okay, so that's some more motivation for the Chinese remainder theorem. We quickly looked at the proof of it more or less. So the theorem says that there is a unique solution to this. Actually, in the proof, you actually get much more than that. You actually get a particular method to construct the solution. And that's more or less what the proof hinges on. Okay. So we'll just quickly look through this. So the way we proved it was by constructing a solution, and then we'll worry about the uniqueness in a moment. So we constructed a solution by generating an x like this. X was generated by this summation formula. It's the sum over all these terms, bi, capital Mi, and capital Mi prime. So what are these numbers? The bi's are just the numbers from the original set of congruences. We have x congruent to b1, b2, etc. Modulo little mi. The capital Mi is the product of all the moduluses except little mi. And capital Mi prime is the inverse of capital Mi modulo the little mi. Okay. And we described how when you see x as that big summation, when you consider x modulo any of the little mi, you consider this thing here, say modulo little m2, well, you see there's a factor of little m2 in every capital M except this one. Capital M1, capital M3, capital M4, all the way to capital MK. All of those have a factor of little m2. So they're all congruent to 0 modulo little m2. So when you consider x, this x modulo m2, everything drops away except for this second term here. And the m2 prime has been chosen so that it's the inverse of m2, capital M2, modulo little m2. So when you're looking at this modulo little m2, this is equivalent to 1, congruent to 1. So you're just left with b2. So it is indeed a solution to x congruent to b2 modulo little m2. And exactly the same argument works. Exactly the same argument works when you consider it modulo any of the little mi. So that establishes that there are solutions. There are simultaneous solutions to those set of congruences. The final last part is just to show that the solution is unique. So typical way to show you've got uniqueness. So you've already established that solutions exist. Now you suppose that you've got another solution. So suppose y now is another solution, another integer solution to this set of congruences. What we want to show is that it comes from the same congruence class as this x, modulo the product of all the moduli. Okay. So we suppose y is any other simultaneous solution. Okay, because it's a solution, both x and y are congruent to bi, modulo little mi. So they're both congruent to each other. So x is congruent to y modulo each of the little mi. Because they're both solutions to x congruent to bi. They're both congruent to the same thing, so they're both congruent to each other modulo each of the little mi. Well, the definition of congruence is that then that the little mi divides x minus 1. But the little mi were chosen, or part of one of the assumptions is the little mi are pairwise coprime. So you've got a bunch of numbers dividing into this number x minus y, but a whole collection m1, m2, m3, and so on. They all divide into x minus y, and they're all coprime. That implies that the product of them divides into x minus 1. Okay. So that's question 5 of exercises 2.1. So just remind you how that result looked like when we considered it. To start, we said if the GCD of, let's say, A and B was 1, if you had two numbers which are coprime, and A divided C and B divided C, that implied that the product A times B divided C. Okay. So you got two numbers A and B that don't share any factors. If they're both dividing into another number, that means the product of them both divides. Okay. We can understand that in terms of prime factorizations. I mean, if A is dividing C, B is, they're both co-prime. It means that the way A divides C, it doesn't use any of the prime factors that are relevant when B divides C, because A and B don't share any prime factors. So therefore, the product will divide C. So what we're using here is just the generalization of that from just two factors A and B to any number of them. Okay? That's a straightforward generalization. So if there is this other solution, y floating around, the difference x minus y has to be divisible by all the little mi, but that means it must be divisible by the product. But if it's divisible by the product, if x minus y is divisible by the product, it means x is congruent to y modulo m. Okay. So this other solution y, this other integer solution, does come from the same congruence class of our little x that we constructed above, modulo capital M. So that proves that that is the unique solution modulo capital. Any other solution comes from that same congruence class, the congruence class of this x. Okay? Now we did an example or two of this in the tutorials. Would you like me to do one more example before we progress on from it? Using it? Yeah? Okay. So let's see what we can do. Yeah, why not choose this one here? Well, yeah, why not choose this one there, part 2. We haven't done that yet. So example 6.4, part 2. So here we're talking about x being congruent to 0 modulo 3, being 1 modulo 4, and x being 10 modulo 23. So we have a capital M, which is the product of all the moduli, which is 12 by 23. 23, 0, and then 10, 2, 6, 4, 276. Capital M is 276. So that's 3 by 4 by 23. The capital M1 is the product of the second and third moduli, everything but the first. So that's the 4 by 23. That's 80 and 12, 92. Capital M2 is the product of the first and the third, 69. Capital M3 is the product of the first and the second, so that's 12. B1, B2, B3 are 0, 1 to 10. There are BI, the little mi. And then remember, capital Mi prime is the inverse of capital Mi modulo the little mi. So we want to get each of these. Actually, we don't actually need, when you look at how the solution X is constructed, we construct X as the sum of all the terms BI times MI times capital MI prime. Because the B1 is 0, that's going to generate that whole first term is going to be 0. So I don't actually need to bother with calculating the M1 prime. Don't need it. Only going to multiply it by 0. So we can save ourselves a bit of time just by moving on to the second one. So M2 prime will be the inverse of 69 modulo 4. So before you start thinking about that, you immediately reduce 69 modulo 4. Reduce 69 modulo 4. 4 times 15 is 60. So 69 is actually congruent to 1 modulo 4. So we're looking for 1 inverse modulo 4. So actually, it's nice and simple. It's just 1. M3 prime is the inverse of M3 modulo little m3. So the inverse of 12 modulo 23. Twelve was already reduced modulo 23, and its inverse is -2. So you're looking for the number such that when you multiply it by 12, you get 1 modulo 23. So it'd be 2. So when you multiply 2 by 12, you get 24. 24 is congruent to 1 modulo 23. Yeah. So you're looking for the number congruence class such that when you multiply it by 12, you get back 1. That's the inverse.
Remembering how to multiply. You can never see that.
Yeah, well,
Like, it's obvious, but I can't see.
yeah. So sometimes they appear easily because the numbers are nice, 12, 23, you know, nice and low.
Well, it sounds like it's 24. That's near 23, but I can't remember what that means.
Yeah. Well, it is. I agree with you. These sometimes it's the easier things that can be frustratingly kind of elusive, kind of. But remember, if you can't just if it doesn't just arrive into your mind what the answer is, remember the ways to obtain it. One way to obtain it is to see it only has an inverse when it's co-prime to the modulus. Okay, it is co-prime to the modulus here. So you can run the Euclidean algorithm between 12 and 23. Euclidean algorithm between 12 and 23, you will get a linear combination of 12 and 23 that is equal to 1. Okay, so that's the smallest non-zero remainder you're going to get, 1. So that's the GCD. So 1 is 11 by, it's 12 minus 11, of course, and then 11 is 23 minus 12. You got 1 12, you got 2 12s, 2 by 12 minus 23. That's your linear combination of 12 and 23 that's equal to 1, equal to the GCD. Whatever the coefficient of the 12 is, that's its inverse sitting there. Okay? Because that's the thing, when you multiply it by 12, you get it's equal to some multiple of 23 plus this remainder. And that's 1. That's the identity. So that's how you know, if the number doesn't appear, if the numbers are awkward, and you know you can't work it out in your head, this is one way to obtain the inverse. Run the Euclidean algorithm, obtain the linear combination equal to 1, and whatever the coefficient of the number is, that's its inverse modulo. Okay. Okay. Oh, and the other way is it's also 12 inverse will also be congruent to 12 to the power of 5 23 minus 1. 1 less than the Euler-Toshin function value on of the modulus. 23 is prime, so its Euler-Toshin value is 22. So minus 1 gets 21. So that's congruent to 12 to the power of 21 modulo 22. Okay, that's not really that easy. That's not easy, you know, any easier. It's more awkward to evaluate, but it is sometimes good to have this understanding about the inverse. That can help as well. So it shows the inverse as a certain power of the number itself. Okay, so that was a good interlude on that. So then at this stage, we've got all the ingredients we need for the solution. So by the CRT, the solution is this x, which is the sum of all these terms, bi, capital Mi prime. The first one has a 0 in it, because the b1 is 0, so don't need to bother anymore with that. The second one is 1 times m2 is 69, m2 prime was 1, and then the third one is 10 times m3 is 12 times its inverse is 2. So whatever that is, it's 69 plus 120, 240. 69 plus 240, 309. 309, so the solution is to this original family up here, let's label that as star. The solution to star is x congruent to 309 modulo 276. And just for aesthetics, we should quote that as being the smallest positive representative, so just reduce it, modulo 276. So it's 33. 33 modulo 276, and we should be able, because the numbers aren't too big, we should be able to verify that that is indeed a simultaneous solution. 33, okay, 33 is congruent to 0 modulo 3. 33 is congruent to 1 modulo 4, so it's 32 plus 1. 32 is a multiple of 4. And it is also congruent to 10 modulo 23. 33. So the Chinese remainder theorem is telling us that 33 is a solution, the integer 33, and also anything else from this congruence class modulo 276. And any solution at all of star, those three things, does come from this congruence class. Okay? It's got a unique solution modulo the product of all the modules. We just saved ourselves a little bit of time there because the B1 was 0. We didn't have to actually worry and work out what M1 prime was. Because we were only going to multiply by 0. So that, okay, any other related queries or questions? Okay, then before we move on, yeah, in tomorrow's lecture, I think we can deal with the material in the next chapter. So before we move on, I just want to draw our attention to the last exercise in those end of chapter exercises. It's this one here. So the other exercises there are other applications of the Chinese remainder theorem. So here is one where we slightly weaken some of the conditions on the Chinese remainder theorem. So to run the CRT, Chinese remainder theorem, we need these moduli to be co-prime to one another. And they will be in our main application of it because they're powers of distinct primes, so they will be co-prime to one another. But it's interesting to ask, well, what happens if they aren't co-prime to one another? Do we have no understanding of how you might solve simultaneous congruences then, or can we understand it? Okay. So this question is kind of prompting you to think about that. For instance, let's just look at this result about a pair of things. So we'll consider this pair of congruences, A modulo n and x congruent to b modulo n. But we're now making no assumption about co-primeness on the moduli. Okay? So the pair of moduli can be any two numbers. They can share some non-trivial factors or not. And this result we're asked to prove here is that this has solutions, meaning simultaneous solutions of those two. Simultaneous solutions if and only if this nice condition that d, which is the greatest common divisor of n and m, if that d divides a minus b, okay, where d is the GCD of n and m. So this is an existence criteria for solutions. They will exist if d divides that. They won't exist if d does not divide that. And then in addition, talking about number of solutions or where the solutions live, what the uniqueness of is, and solution is unique if it exists. Unique modulo, not the product of the two moduli. It was the product in the co-prime case, the kind of corresponding notion in the not necessarily co-prime case is the least common multiple. When n and m are co-prime, then their least common multiple is just the product. It's just the product. But in general, the kind of similar kind of thing is the least common multiple. The smallest number that's simultaneously a multiple of n and m. So an important point to note about this thing that we're asked to prove here is that this whole thing is equivalent to the CR, or it reduces, or it's equivalent to the CRT when the GCD of n and m is equal to 1. So if it was, so this statement, this kind of statement here that we're going to try and prove, this if and only if statement here we're going to try and prove, it's stated for any n and m, but in the special case when n and m are co-prime, it exactly corresponds to the Chinese remainder theorem. So if they are co-prime, it means their greatest common divisor is 1. So it's saying solutions exist if and only if 1 divides the difference. Well, 1 divides everything. So it's saying solutions will always exist. Okay? Because this divisibility criteria will always be true. Because the d will be 1 if n and m are co-prime. So solutions, if we believe this blue statement, solutions will always exist when the GCD of n and m is 1, and they'll be unique modulo the least common multiple. Well, when the least common multiple of n and m, when they are co-prime, is just their product, n multiplied by n. And that's exactly what the Chinese remainder theorem says. So the solution is unique modulo the product of the two. So that means this statement in blue here, the one in the exercise, it is a generalization of the CRT. It's a more general statement, which in the special case where n and m is co-prime goes back exactly to the CRT. So it's a weakening of the CRT. It's more widely applicable, so you can apply it now to cases where the moduli aren't necessarily co-prime. Okay. So let's have a go and think about how we might prove this. Are any questions just about the statement of it to begin with? Just about what it's saying. Okay. So this is question 5. So it's an if and only if statement, so it deserves to be proved in both directions. So the first direction we're going to do is we're going to assume that we've got a simultaneous solution. First, we're going to assume a simultaneous solution exists. Simultaneous is a hard word to spell. So, i.e., there exists some integer x, and x is congruent to a modulo n, and x is congruent to b modulo m. These are not questions anymore, these are statements. There is such an x, and it satisfies both of those. It's a simultaneous solution. I.e., there exists multiples q and r. I mean, what does it mean for x to be congruent to a? It means x is equal to something times n plus the remainder a. And it also, what does it mean for x to be congruent to b? It means x is some multiple r of n plus a remainder b. Okay, these immediately give us equations for a and b. A is x minus qn. B is x minus rm. And the result we're trying to prove says something about the difference, a minus b. We're trying to prove that the greatest common divisor divides the difference. So the most natural thing to form out of this is to form the difference a minus b. So this implies that a minus b, well, a nice thing happens when you do a minus b, the x's disappear. X's cancel, and you've got r minus qn plus rn. Remember, we're doing the only if direction, so we assume solutions exist. We're trying to get to that this implies D divides A minus B. Yeah, we're trying to get to that stage. Bit of a gap here. What is D? D is the greatest common divisor of N and A. But here we have A minus B as a linear combination of N and A with integer coefficients, Q and R, minus Q and R. Well, we've all, we've got should have a good understanding of common divisors and greatest common divisor. Just the fact that D is a common divisor of N doesn't necessarily have to be the greatest one for this to work. Okay, just because it's a common divisor, divides N, divides M, therefore it divides this linear combination. That was a basic property of common divisors. That implies D divides A minus B, as A minus B is a linear combination. Linear combination of A and of N and M, and D is a common divisor of these. Okay, so that's the solutions exist implies D divides A minus B. Now we got to go the other direction. So now a separate argument. We assume D divides A minus B, where D is the GCD of N and M. Now we're looking for simultaneous solutions. I'm looking for an X that solves this and simultaneously solves this. Well, X solves the first congruence if and only if X is congruent to A mod N, i.e. if and only if there exists a Q, an integer Q, such that X is Qn plus A. Such a number such as this, Qn plus A, such a number also solves the second congruence if there exists an R and Z such that this X, which is congruent to A modulo N, is also congruent to B modulo N. So in other words, if Qn plus A is equal to Rn plus B. Or to rephrase this again, X is a simultaneous solution if there exists Q and R integers, obviously, if there exists a Q and R such that this is equal to this. So A minus B is equal to minus Qn plus Rn. So in other words, we get this statement. Now we haven't used the assumption yet. We assume that D divided A minus B. We haven't used that yet. We just started off investigating simultaneous solutions. If X is a solution to the first one, it's of this form, Qn plus A. If it's a solution of the second one, it means it's simultaneously of this form, Rn plus B. How can those two happen at the same time? That's the same as saying A minus B is something times n plus something times m. So in other words, a minus b is a linear combination of the two of them. And we want to know that such a linear combination exists. Okay? The solution exists if simultaneous solution exists if there exists the Q and R that make this happen. Okay? But we know that there exists, I won't call it Q and R, I'll call it an S and T such that D, the greatest common divisor, is Sn plus Tn. And if D divides AB, which we assumed it did, that implies there exists a gamma such that A minus B is equal to gamma times D. So that implies that A minus B, by substitution, if A minus B is gamma times D, that means it's also gamma S times N plus gamma T times N. We just said a moment ago that simultaneous solutions exist if there exist these coefficients that give you A minus B is a linear combination of N and M. Well, here they are. Here's the gamma S, here's the gamma T. They're coefficients of N and M that give you a linear combination of N and M equal to the difference A minus B. So a solution does exist, simultaneous solution does exist with this minus Q we were looking for being gamma S, and this R we were looking for being, sorry, not delta, gamma, being gamma T. So that proves the if and only if bit. Okay. We assumed at the start that solutions existed. We were able to conclude that D divided A minus B. Then we assumed that D divided A minus B, and we were able to prove that solutions existed. The remaining part is to prove the uniqueness modulo the least common multiple. Thirdly, we prove the uniqueness part. So we should assume X and Y are two solutions, two simultaneous solutions. So X is congruent to A, and this is congruent to Y modulo N. And X is congruent to B, and Y is also congruent to B modulo N. So X and Y are two simultaneous solutions to these two congruences. So that implies that, or that's true if and only if X and Y are congruent modulo N, so if N divides X minus Y, and M divides X minus Y. I won't say equivalent because they have to be specifically congruent to A and B. So, but if X and Y are two simultaneous solutions, it means X is congruent to Y modulo N, and X is congruent to Y modulo N. Or to just put that in English, how would you say that in English? It means X minus Y is a common multiple of N and N. Simultaneously, a multiple of N and a multiple of N. Okay. And we proved back in chapter 2, probably was, that the least common multiple, similar to the GCD, the least common multiple has a special property. not only is it the smallest common multiple, it has this property that it also divides every other common multiple. Just as it's the same kind of property, it's true for the same reasons that not only is the greatest common divisor the biggest thing that divides the two numbers, every other common divisor divides the greatest common divisor. Well, the least common multiple is just looking at things from above rather than below. It's the smallest thing that is a common multiple of n and m, and anything else which is a common multiple, the LCM divides those two. Divides it. Anything else that is a common multiple of the two arguments, the LCM divides. So there's an x minus y as a common multiple of n and m. So that implies that the LCM of n and m divides x minus y. So just to refer you back to the result, that was question 13 of exercises 2.3. Many useful properties are, in the exercises as well. So if x and y are two solutions, means they're divisible by the LCM, so it means they're congruent to each other modulo the LCM. So we proved a bit the condition, the if and only if condition for existence of solutions. And now when solutions do exist, they actually all come from the same congruence class modulo the least common multiple. So that proves this generalization of the Chinese remainder theorem to congruences. Okay, that's a good place to stop. Next lecture, which will be tomorrow, we'll move into following chapter, polynomial congruences 2, and we'll start to see, well, after understanding things a bit, we'll finally see how the Chinese remainder theorem kind of glues everything together and allows us to solve the general congruences. Okay.